My name is Vasha DuTell, and today I'm going to talk to you about exciting new results from a recent project studying natural vision, and in particular, the properties of the visual signal's power spectrum, both in space and in time. The crux of this work surrounds the goal of understanding the effect of various components of natural motion that contribute to the signal that reaches the retina. When we consider what types of motion these are, one often thinks first of environmental motion, or the motion of the world around us in the absence of our own motion. However, another important contributor to the motion we perceive is the motion introduced as we run, jump, and otherwise move within our environment. Relatedly, given the location of the retina in our heads, head motion in the absence and in addition to body motion is a distinct contributor. And finally, a favorite among vision scientists, our eyes combine with all of the previously mentioned motion categories in a multitude of incredibly coordinated, precise patterns, contributing to an entire, if not multiple, additional categories of motion on the retina. So what is the effect of these various types of motion on the signal that reaches the retina as we go about our daily lives? With this work, we are interested in understanding not only how these motion types contribute separately to distinct motion on the retina, but also how they combine together, working in synchrony to create the final signal presented to the photoreceptors of the retina. In this work, we focus on a basic property of dynamic scenes, the joint spatiotemporal power spectrum. A seminal piece of literature in this area is the 1995 paper by Dong and Attick, which reported the spatial and temporal power spectrum of natural video. The authors used a setup of cinematic and nature videos, including scenes from action movies. Calculating the spatiotemporal power spectrum for these videos, they found that, matching previous findings for static natural images, spatial frequencies follow a power law distribution. Separating the spatial frequency spectrum into different temporal frequency components, they found that lower temporal frequencies have the highest power and fall faster, with increasing spatial frequency, bounded by 1 over the frequency squared. Correspondingly, high temporal frequencies fall more shallowly, with power bounded by 1 over spatial frequency below. In the temporal frequency domain, the authors found an analogous relationship, with low spatial frequencies contributing the most temporal power, bounded by 1 over temporal frequency squared, and high spatial frequencies bounded below by 1 over temporal frequency. We aim to extend this work in 3 main ways. First, we aim to study a variety of natural environments that are representative of a day in the life of the modern human. Second, we have designed a method to include and differentiate additional types of ego motion that contribute to the signal reaching the retina. And third, with modern high-resolution and frame rate camera equipment, we can extend the spatial and temporal frequency axes beyond what has been previously studied to explore the scale dependence of these relationships. To collect this data, we have designed and built a custom head-mounted camera setup. This device consists of a 200 frame per second industrial camera, which can collect the scene at high speed and resolution. We also incorporate an Intel RealSense camera, which collects both RGB and depth streams for the scene. The setup also includes the Pupil Labs binocular eye tracker, allowing registration of the gaze point in the scene. Finally, we utilize 2 RealSense trackers mounted on head and body to capture the wearer's ego motion. With the goal of our data being representative of a day in the life of a modern human, we have designed a set of tasks that sample a variety of visual experiences encountered in daily life. The data I will show you today is comprised of 6 near to mid-distance tasks. These include having a conversation with another person, making a sandwich, which requires manual manipulation, and reading a book. In addition, given the increasing amount of screen time humans are exposed to, we designed a set of 3 representative tasks that involve both active and passive interaction with screens, using a computer, playing a cell phone game, and watching clips from the same action movies used in the Dong and Attick study. In order to separate out ego motion from environmental for each task, we collect data in 2 different ways. First, we have a static camera setup where we place the camera rig on our mannequin, who observes the task being performed from a tripod. We also collect data for the same task, while a subject wears the setup and performs each given task, shown on the right. Importantly, we position the mannequin and tripod so as to be close as possible to the position of the subject's head so that the mannequin's view of this task is as similar as possible to the subject's view. Here you can see the RGB camera view for the make a sandwich task, performed both in front of the static camera on the left, as well as with the camera mounted on the subject's head on the right. As you can see, there's a clear difference in the motion content of the 2 videos, simply due to the head and body movements introduced by the subject. We will see later how this motion alone impacts the resulting power spectrum for the 2 movies. Because we've included binocular eye tracking in our device, we are able to, with careful calibration, locate the subject's position of gaze within the frame for the head-mounted condition, as well as depth information. Here is an example of the subject's eye position during the movie and their gaze point located within the video frame, shown on the right. Note the large saccades that quickly change the gaze point within the scene, the smooth tracking that follows moving objects, as well as the smaller adjustments that fix gaze on the bread tie, for example, compensating for the drifts in image space due to head motion. These additional movements will affect the spatiotemporal statistics dramatically, and we will soon see exactly what this effect is. We can use this data to differentiate between three motion conditions. The first, world, shown on the left, is video data taken from the static camera, which includes environmental motion only. The second, head, in the middle, is video taken directly from the head-mounted camera, and in addition to environmental motion, also includes body motion and head motion. Our final condition, retina, on the right, is video taken from the head-mounted camera with spatially and temporally registered eye motion overlaid on it. This includes all of the motion categories: environmental, body, head, and eye. This condition is representative of the signal sampled by the retina. To analyze these three motion conditions, we first extract from each of these larger videos 512 pixels squared by 200 frame chunks of video. This corresponds to about 15 degrees visual angle and 2 seconds. For the world and head conditions, shown on the left and middle, we sample chunks from random temporal locations, but spatially fixed in camera coordinates at the center of the two videos, respectively. For the retina condition, we perform the same temporal sampling, but match the spatial location at each time sample to the measured fixation location of the subject, and progress the video and fixation location together. These result in movies that incorporate progressively more motion types layered upon each other. Here's an example movie chunk for each task and condition: world, head, and retina. For each task and each condition, we extract 100 samples of temporally random movie chunks. For each movie chunk, we apply a cosine window to negate edge effects, then calculate the 3D Fourier transform, calculating two spatial frequency dimensions as well as time, and square to get the power spectrum. We then collapse over the two spatial frequency dimensions by taking a radial average spatially. This results in a two-dimensional power spectrum with space and time as the two axes. We calculate both the average power spectrum per task and finally inter-task means. These inter-task grand means give us the power spectra for each given motion condition. For the world condition, our measured power spectrum for natural tasks bears strong similarity to the previous Dong and Attick work. These similarities extend to spatial and temporal frequencies higher than those previously measured. Both spatial and temporal spectra show a steep fall bounded by 1 over frequency squared for lower frequencies and shallow drop-off bounded by 1 over frequency for higher frequencies. This results in a joint spatiotemporal power spectrum with a curved shape. When we incorporate body and head motion, we see much more power in the mid-level spatiotemporal frequencies than before. This translates to a distinct whitening effect for low to mid-temporal frequencies. These correspond to a joint spatiotemporal power spectrum, which has a box-like shape. And when we add retinal motion in, we see further boosting in the highest temporal frequencies, up to the Nyquist limit for our 200 Hz camera. For our high and mid spatial frequencies, we have reached nearly equal power in all temporal frequencies. The corresponding joint power spectrum becomes extended, becoming much flatter. These data support the hypothesis that head and large-scale eye motion contribute to a whitening effect on visual signal, and that the frequency distribution of the signal on the retina tends toward equal power in the temporal frequency spectrum rather than falling as power law. These results for head and large-scale eye motion complement previous results in the literature, which show whitening effects due to finer-scale drift eye motion. To separate out the effect of these two ego motion types, we take the world power spectrum as a baseline and subtract it from the power spectra for the eye condition shown on the left, for the head condition shown on the left. We do the same for eye motion shown on the right, subtracting the world condition as a baseline. This shows us where in spatiotemporal power space the signal power is changing. We see that overall, these changes in power from ego motion are primarily from boosting effects rather than attenuation of signal. Equivelocities, which run along the positive diagonal, indicate which velocities are being introduced with motion. For head motion, this boosting occurs in a central region in spatiotemporal frequency space, corresponding to mid-range velocities. For eye motion, this boosting is only in high temporal frequencies at low spatial frequencies, which corresponds to high velocities. In conclusion, we validate the finding that the spatiotemporal power spectrum of natural video follows a power law, and we find that this extends to natural tasks. However, we find that for signals modulated by ego motion, while spatial frequencies continue to approximate following with the power law, temporal frequencies become whitened due to a combination of head motion, which boosts a broad range of frequencies, and eye motion, which boosts high temporal but low spatial frequencies. These results have important implications for both understanding the role of ego motion as a modulator of visual perception, as well as for theoretical and signal processing studies of early vision, which will benefit from knowing this important property of the input to the first circuits of the retina. This work is part of a larger dataset currently being built, which combines high frame rate video collection with eye position, depth, and motion information. Having such data opens a world of possibilities for further statistical analysis and also provides a dataset for experimentalists and theorists to utilize that is representative of a day in the life of the human retina. Thank you all for your attention. I would like to acknowledge those who have given valuable knowledge and feedback on this work. Thank you also to our generous funding sources who made this work possible. Thank you.